Yeah, welcome back, and we're gonna continue our discussion of fluid mechanics. So in the last video, we were just talking about manometers and went through an example, but if you haven't gone through that, don't worry, as long as you got a basic understanding of how manometers are supposed to be read and how they work, pretty much should be okay. Alright, so moving on. You want to talk about the frictional forces that are in the what do you call that? Yeah, frictional forces that are encountered in pipes and pipes and valves and all that kind of stuff. Yeah, because we have neglected this F term on the right hand side before. So now we want to discuss about how we actually find out this F. What you will see happen in fluid mechanics is that people will usually divide throughout by volume. So we'll take a volumetric basis. So this V will be gone, and this will be just rho, which is density. Rho and this F will be some force, some energy per unit volume attributed to frictional forces. Okay, so on a per volume basis, that's what you get. And yeah, so the classic example, just gonna delete this off. We're gonna have pipe. Okay, you're gonna have some flow from point A to point B. This gives us a blue color, and you'll have some pressure measurement here, some pressure gauge. Then you're gonna have it called P1. Let's make it bigger. Maybe let's put 24 font size. Yeah, perfect. You have some pressure gauge P1 here, and then you have some other pressure gauge, and it's gonna give you another reading P2. So this is a pipe with the same cross-sectional area over here and here, and I'm gonna read the two pressure. Alright, and since the fluid's incompressible, okay, incompressible and same elevation, then the continuity equation means VA goes to V at B when cross-sectional area is the same. Okay, so these two terms are going to disappear, these two terms are going to disappear, and then you're left with this, where you have the frictional force. The frictional force is just measured, or the energy loss due to friction is just measured by the pressure at A. This should be PA, this should be PB, A and PB. I wonder if I did it for my old ones, but never mind. Regardless, so if we have some pressure at A, or P1 in this case, and then we have P2 in this case, we can just take a direct measurement and that will have a frictional force term. And how would people usually write this down? Now this frictional force term, people would like to write K times half rho V squared. Why do they like to write it in this term? Because you see, it's easy to relate. This K is how many times of the kinetic energy is being lost as friction. So how people would like to write is in this manner: PA minus PB equals to K times half rho V squared. Then what people will usually do is that they will have some experiment in the pipe, have a flow, and then they'll measure the pressure drop. Okay, they'll measure the pressure drop, P1 and P2. Then they'll substitute into here. Then they'll find, there'll be a certain fluid velocity. They'll have some kind of flow meter for that. That's why the Venturi flow meter is useful. Or some other kind of flow meter is useful. Then they'll take the pressure difference between this and this point and this point to find the pressure drop across. Let's see whether I can find a nice arrow shape or something. Oh, never mind. Across here. So they'll find the pressure drop across here. Then they'll find the resulting K value. Alright. So that's what the procedure is usually like. And it does not matter whether it's a pipe. It can also be, for example, a valve. So a valve is usually drawn like this. Then you'll have and this is how it usually will look like. Pull this up and there you go. A valve will look like this. And well, depends on how you turn the valve. It can be a gauge valve, globe valve, all kinds of valves. Alright. And this valve will have a particular K value based on the pressure drop between P1 and P2. Of course, you can do it, you can do it for anything as well. You can do whatever you want. So I'm just going to squiggle some lines here. You can do it for whatever component you want, as long as the flow that is coming in here is the flow that's going out here, and then there's no other flow that is coming in here. So no other kind of flow. Okay. Well, it's getting messy, this diagram. I'll just copy and paste. Okay. Yeah, it can be anything you want, any component, and they will test. And then they will find the corresponding K value. This is a simple concept to understand. And if you look at Perry's Chemical Engineering Handbook, alright, I'm going to search. Oh man. Yeah, I'm gonna search where am I looking at? Yeah, I'm just gonna search a very particular one. Velocity, no. Okay, I'm looking for hydraulics. No. Frictional losses in pipeline elements. Okay, this is where we are. Yeah, this is what I'm looking for, table 6.4. So I'm just gonna copy and paste it down. Okay, just ignore that stop sign. Okay, 10 minutes in. Okay, I shouldn't make it too long, my video. Okay, additional friction loss, equivalent number of velocity hits, and then you have this big K here. So this big K is of a similar thing to what this K is here. But then you'll probably ask me, hey Theo, it's great that we have K's and everything, but it looks kind of fishy, doesn't it? Suppose we have this case, and then you tell me that the pipe is bigger, or the fluid changes from water to oil, or some other things changes, or even like okay, even for the simple case of a pipe. All right, for this pipe, okay, for a pipe, if the length is longer, then we're going to have more frictional losses, right? It cannot be a constant K. So isn't it going to be very difficult that we are going to have to test the K value for every unique fluid situation? And if that is so, doesn't that mean we have to do like millions of experiments to find out all the K values that is possible? And furthermore, if like you have to have a 50 meter wide or 50 feet wide, about 10 meters, like a pipeline, you know, pipeline for oil pipelines, and then you want to go and test for K values over like 1,000 miles of pipe, or 1,600 kilometers of pipe. Well, if you really want to build a test apparatus that big, you might as well just build the pipeline itself. All right. Now, how are we going to find these K values and estimate the frictional losses before we build the actual thing? Now, these are some of the things that engineers need to think about. And indeed, we do need to think about such things. That's why finding these K values isn't always as simple as this, because there are some practical difficulties when it comes to building this test apparatus. Especially if this pipe was like 1,000 kilometers long, or you have a complex piping system with many valves and everything, it's going to be very difficult. So we have to find a systematic way to estimate what the K values are. And of course, you would be right if you had thought that, hey, it cannot be a fixed K for every kind of a fluid. So actually, this K that you see here is not exactly this K. It would be, this K would be this small k equals to some function of this big K, then some of the fluid properties, and then maybe the pipe dimensions, etc. Now the tricky thing is to find a formula that describes all of this, so that we can find our appropriate K values. All right, for maybe long and short pipes of with different fluids flowing inside, then we can start telling how strong do our pumps need to be, how much energy do we need to give to the pumps in order to keep it running. So yeah, that's the problem that we have now. And in the next video, we're going to discuss some of these interesting techniques to help us find out how do we find these special K values that we are talking about. Now, thanks for watching. I'll see you guys in the next video. Bye-bye.